Welcome back to another episode of Tech Talk Today. I'm your host, and today we're diving into a topic that's both complex and crucial: the importance of end-to-end correctness in communication systems and the challenges that come along with it. We'll look at how low-level mechanisms like TCP and Ethernet play a role in maintaining data integrity, while also discussing why these alone aren't sufficient. So grab your headphones and let's get started. Communication systems, it's easy to overlook the various layers that make up the entire stack, from the physical layer of Ethernet to the transport layer of TCP. Each layer has its own functions designed to ensure that data is transmitted accurately and efficiently. For example, TCP includes a feature called duplicate suppression, which allows it to recognize and eliminate duplicate packets sent over the connection. Processors also offer exactly once semantics, ensuring that messages are processed without duplication. But here's the catch. While these mechanisms help, they don't completely eliminate the risk of duplicates from the user's perspective. If a user submits a request and it times out, they might resend it, which can lead to duplication issues that TCP and database transactions alone can't resolve. To truly tackle this problem, we need an end-to-end solution that tracks a transaction identifier from the client all the way to the database. This approach is vital because although low-level features like TCP's duplicate suppression are helpful, they don't guarantee that the application will be free from data loss or corruption. Now let's shift our focus to data integrity. While low-level features can detect packet corruption during transit, they often fall short when it comes to identifying software bugs at either end of the connection or problems with data storage. Think about it. Your home Wi-Fi password protects against snooping on your local network, but it doesn't guard against threats from elsewhere on the internet. Similarly, while TLS SSL secures your connection to a server, even with strong low-level reliability mechanisms, we can't overlook that applications need to implement their own fault tolerance measures. This can be quite challenging because high-level fault tolerance mechanisms are often complex and counterintuitive. Many developers might assume that using a data system with robust safety properties, like serializable transactions, is enough to ensure data integrity. Unfortunately, that's not the case. Applications must actively implement measures like duplicate suppression to truly protect against data issues. Let's talk about the cost of transactions. Distributed transactions can be expensive, especially when they involve multiple storage technologies. When developers avoid using distributed transactions due to cost, they often end up re-implementing fault tolerance mechanisms within their application code. This can lead to a higher likelihood of errors, lost data, or corrupted information. The reality is that reasoning about concurrency and partial failures is tough, and many application-level mechanisms may not function correctly. So how do we ensure correctness in our systems? One approach that's been discussed in the context of unbundling databases is using request IDs for end-to-end duplicate suppression. This concept can be extended to enforce uniqueness constraints across various applications. Consider usernames, email addresses, and booking systems. All of these require unique identifiers. If multiple requests come in for the same username, the system must determine which request to accept. This is where consensus comes into play. If several concurrent requests are made with the same value, the system needs to decide which operation is valid and reject the others. One common method is to designate a leader node to handle all requests, but this can create bottlenecks and points of failure. If that leader fails, the system must deal with the consensus problem all over again. To maintain uniqueness, we can partition requests based on their identifiers. For example, if usernames need to be unique, we can partition by a hash of the username. However, this approach rules out asynchronous multi-master replication, as it could lead to conflicting writes. To immediately reject any writes that would violate constraints, synchronous coordination becomes necessary. Let's take a closer look at enforcing uniqueness constraints using a log-based approach. In this scenario, we treat every request as a message appended to a log partition based on the unique value. A stream processor can then read these requests sequentially, ensuring that each one is processed in the order it was received. If a username is available, it gets recorded as taken. If not, a rejection message is sent out. This method scales well to high request throughput by increasing the number of partitions, allowing each to be processed independently. However, as we add more partitions, we need to consider how to manage atomic commits across them. For example, when transferring money between accounts, we want to ensure that both the debit and credit instructions are executed together. By logging the original request with a unique ID and deriving the necessary instructions from that log, we can avoid the need for a distributed transaction. In this way, we achieve the same correctness properties, ensuring that every request is applied exactly once to both accounts, without relying on complex atomic commit protocols. If a stream processor crashes, it can resume processing from its last checkpoint, and thanks to the deterministic nature of the processor, it will produce the same instructions again, which can be easily deduplicated using the end-to-end request ID. As we wrap up this discussion, it's important to remember that while low-level mechanisms offer a foundation for reliability, they aren't enough on their own. Applications need to take proactive measures to ensure end-to-end correctness. By implementing unique identifiers and leveraging log-based processing, we can create systems that not only maintain integrity, but also scale effectively in a distributed environment. In this episode, we've explored the intricate relationship between low-level reliability mechanisms and the necessity for end-to-end correctness in data systems. We've seen how applications must implement their own fault tolerance measures to avoid data corruption and loss. As technology continues to evolve, the challenge of ensuring data integrity remains a critical focus for developers and engineers alike. Thank you for tuning in to Tech Talk Today. If you enjoyed this episode, don't forget to subscribe and leave us a review. We'll be back next week with more insights into the world of technology. Until then, keep questioning and exploring the fascinating landscape of data systems.